Okay, this is the video solution for homework number 6, Lab 53. And there are two problems. Uh, People in Lab 53 have to submit problem 1, and I'll do a second video for Lab 54, and they have to submit number 2, and I'll do the video for problem number 2 in that section. Okay, so if you're in 53 and you want to see how problem 2 is done, just watch the one for Lab 54. Now, uh, this homework is due after you come back from the summer break. Remember, you're coming back on Monday, June 28th, and this is due Wednesday, June 30th at 12 noon. Okay? Now, also, we don't need the PDF file for this particular lab. Okay, just give us the part and the analysis. That's all. No PDF. Okay, so the problem that you guys have to do is a structure like this. This is a folded sheet metal made out of steel. This one is made out of steel, and the thickness of this thing is 1 inch. And this edge is clamped. This entire edge is clamped, and you're subjecting to a compressive load. And what you would like to do is what is the buckling load, the linear buckling analysis. Basically, you're asked to model this problem with parabolic shell elements, and the details of the shell are given here. Okay. All right. So let's go ahead and make it. Now remember, this is 3 by 10 by 20. Okay, so I'm going to make this section, this section, 3 by 10 by 3, and then extrude it. Okay, so let's go ahead and make it. We are doing part. Immediately, we're going to save this. File, save management, save as, desktop, oops, not desktop, new folder. This is Lab 53, problem 1. Okay, I put everything in here. So on that plane, I will sketch something that looks like that. By the way, do not use symmetry unless you know exactly what you're doing. Uh, when it comes to buckling and natural frequency calculation, avoid using symmetry, as I said, unless you know exactly what's going on. And that takes a little bit of time and knowledge and effort. This one and that one, control, and this one, make it symmetric. Okay, let's put some dimensions here. This is 3 inches, and this is 10 inches. Okay, exit, and then extrude it. Now you're in part design, you can extrude it, so you go to generative shape design, and then you find the extrude right here on the surfaces. Was it 20? That was 20 inches. There's my folded sheet metal. And because of the way I made it, there's no issue of the having duplicate nodes on the two sides of the seams, etc. This is good. You don't have to do anything. Now, apply material to this metal. This is made out of steel, and on that part, we say OK, and let's save this. And now we're going to go to generative shape design. And immediately we have to do a static analysis. Whenever you have to do buckling, the first step is a static analysis. So let's mesh it with shell elements. And I said use parabolic, size 2, say OK. And then the thickness, you're told that the thickness is 1. I believe it says thickness of 1. Yep. Okay. That's good. Let's save it. File, save management. This is the analysis, save as in that folder, which says Lab 53, problem 1. All right. Okay, let's clamp this in. Clamp this and that and that. And then let me hide this sketch on that side for you. And then you have to apply a dummy load of 1 on these three edges. Total, these three edges, see, dummy load of 1. So you apply a load on this and that and that, all three of them, a load of total -1. -1 mean, no, actually this is not -1. It should be in the direction y, right? So let's change this thing to 0, and in the direction y, a dummy load of 1 on these three edges, okay? Because the load is applied in this direction, that's in direction 1, and it's a dummy load, 1, compress, which will compress this, okay? You say okay? So you run it, and nothing exciting is going to happen. This is going to compress without showing any signs of buckling. But the first step is to do a static analysis with dummy load. Okay, so let's see now. There we are. Well, I mean, obviously, because of the fact that this is not symmetric, there's no problem. It will not completely compress, but it will look like this. Okay, there's nothing wrong with that. Okay, the combination of bending and compression, that's fine. So deactivate that, and then we're going to do and insert the buckling load. Insert a buckling case. It asks you, where is that static solution that you just ran? It's asking for reference solution. So you go there, expand this thing, and you select it right there. This is your reference solution. It's asking, and you say okay, and all you have to do is to run it. That's it. That's it. So let's look at the different buckling modes and loads. There we are. Okay. So if you double click on this, you will get the modes, the buckling modes, and the factor. In other words, the one dummy pound that you applied here, multiply by that, it says 2 million, what is that, 2 million pounds, okay? And then the next buckling mode looks like this. See that? And like that, and like this, etc. So these are all the different buckling modes. The one that we want is the smallest one, okay? And it looks like this, okay? And that doesn't surprise you, because this is the kind of thing that happened when you were dealing with Euler buckling in, for a beam, okay? Now, this is the total buckling load, 1 pound times this, which is 2 million. Now, remember, in real life, this is not a conservative estimate. In other words, the part will fail. In all likelihood, will buckle well below the slope. Okay, but this is what linear buckling analysis predicts. Now, what I'm going to do in Lab 54, or your second problem, basically, I'm going to repeat this thing, but I use the parabolic solid elements. See how it compares with this. Remember, this was almost 2.3 million pounds. Okay, so that takes care of this. Now we're going to do another video for Lab 50.